Hi, my name is Arun Venkatachar. It's a pleasure for me to deliver this year's keynote for the ISQAD Symposium 2021. The topic I'm going to talk today is about the confluence of AI when it comes to EDA for solving chip design problems and also the complexity involved in developing software engineering and how AI can come to the rescue. A little bit of introduction. I'm currently the head of Synopsys Center Engineering. This is a charter where I am the corporate owner for driving the artificial intelligence strategy and execution, as well as building some of the engineering blocks that are required for the cloud opportunity. I'm also the corporate owner for driving all of Synopsys engineering operations. I've been in EDA for about close to 22 plus years, primarily focused on various aspects. 1, product development. 2, customer engagement. 3, operations. 4, spending a lot of time on AI, ML, big data, and cloud in the last 4 or 5 years. Prior to my work at Synopsys, I was part of Precedence and also worked at a research institute back in India. I have a master's degree in computer engineering and been publishing some papers and patents in the area of compilers, distributed computing, and AI. So the two topics are really about looking at how AI and ML can aid chip design. Here the focus will be how can AI and ML help us basically solve some of the complex problems that are posed from a chip design industry, especially to improve the time to market, quality of results, cost of results, and look at how it can help us with productivity and efficiency. The other aspect of my talk is to also look at how AI ML can help us to improve our quality, productivity, and efficiency when it comes to product development. While some of the examples I'm going to talk about are related to how AI ML can help us in the software engineering for product development of EDA products, the same parallel can also be established for RTL development because most of the challenges that you see there are very similar to that one that you would see with software engineering. So with that, let's get started. So as you all know that the reality of chip design is a very tough game to play. The parallel I have here is that of a chess game where AI ML was used to solve some of the search space explorations, right? And then if you look at AlphaGo, Google tried to solve a similar problem, but a much more complex game when it came to the number of states that they had to explore for solving the AlphaGo problem. Now put that in contrast with some of the latest things that are happening today with respect to placement. The number of states are significant that one has to explore because you're talking about billion transistors, especially with the new AI chips, you're talking about multi-billion transistors. So the complexity is enormous when it comes to playing this game. The challenges that are there in today's design, the deluge of them. Think about in the area of verification, running too many tests, managing the coverage closure, looking at opportunities to ensure debuggability is better. Then move to design, where you have to deal with placement, routing, complex rules that you have to play with, the PPA targets. Then you go into manufacturing, where you have to deal with mass synthesis, yield management. As you can see, there are so many different challenges that are posed today. And EDA is one of those areas where many of these problems are NP hard. And one really has to come up with unique ways to solve them. We have been very focused on solving these problems today in EDA through a whole bunch of algorithms. And we do a lot of heuristics to solve those problems. Now, in the past, we have been spending time on building point tools or products that solve these kinds of problems. Now, in our arsenal today, we have AI, big data, and ML to come to the rescue in a form. So really the industry is looking at how can we leverage these technologies to bridge the gap that we have today to go to market. An idea that one starts in one's head, by the time it goes to a final product, it can be many, many months to years in terms of chip development time. Can AI and ML help us in trying to close that gap is really what we're looking at. And this, I'm going to give some examples. So let me start with the background first. The value of data is going to be shown here through this representation I want to go over. Typically, the past few decades, as I mentioned, the RTL to GDS flow involves a whole bunch of products put together as a flow when it comes to solving the whole tape-out challenge. Now, really what's happening is these products, many of these products which are in these flows generate a ton of data. Literally, if you abstract it out, algorithms that are there today in these products are actually generating a ton of data. But the paradigm shift that's really happening is data has become the epicenter lately. The amount of data that we generate in these chip design flows are quite massive. Now, if you really look at AI ML, it's about looking at it from a perspective of given data, can you generate an algorithm that can predict the outcome? So literally, the data is starting to decide algorithms as we look at AI and ML perspective. Now, could you call that a disruption? Absolutely. But let's look at some cases where can it apply and where it cannot. Now, at Synopsys, we look at using AI ML from a concept of three different vectors. One is about enabling AI chips, which is not the focus of this talk. The other one is about AI enhanced tools. How can AI ML can be embedded into our products to make them smarter, to make them better in terms of productivity, efficiency, and turnaround time in algorithms. And on the right hand side, you see the AI driven applications. These are things around the flows because data is not just within the tools, it's data is around the tools, around the flows. And how can AI help us? In the middle of it is about platforms that they work on in terms of could it be Synopsys platforms in design, verification, continuum, as well as silicon engineering, but also AI platforms because the world of AI brings in its own challenges of deployment and one has to invest time in building a good data diligence. And as you can see, AI ML doesn't differentiate between these vectors. They look at data. So it pretty much looks at the entire flow, as you can see the bottom chart, all the way from design specification to tape out. It can apply to many aspects of this flow. Now let's take a look at a few examples. So here you see the case of Synopsys investing many projects in the areas of AI enhanced products on the left and AI driven applications on the right. As you can see, AI ML can help us build better optimizations, better predictions, better classifications, and better schedulers. And we apply them at various different stages, as you can see on the left. And on the right, AI ML can help us build better flows because there's a lot of parameter tuning that can happen, better debug so that you can do faster root cause analysis, better planning in terms of flow planning, etc., where you can learn from one stage and pass it on to the other, and also help with your productivity tools that we build across the spectrum. Now, when you look at a few examples, I'm showcasing one of them here. This one won the World Electronic Award. This is about a product called DSO.ai, Design Space Optimization. It solves a very complex problem of PPA search, right? Power, performance, and area. It's always been done manually quite a bit. The tools, of course, help you to get to some extent. And then there's a lot of manual work involved in that convergence between the power, performance, and area. And here we use reinforcement learning to build a solution which actually cuts down a significant amount of time from an engineer to actually converge faster. We are talking about from few months to days. And this innovation has helped us to find areas that humans could not do before. It's not only converging fast, but it's also finding new convergence points that never could have been reached before. So this is definitely revolutionary. We call this the autonomous AI design, where we really want to look at such explorations that exist today in our EDA domain and apply such technologies. Another example of a use case is in a product called VCLP, which is low power, where tons of violations are emitted today. And AI ML can be used to intelligently cluster them, mark them into smart groups, and we use root cause technology to basically eliminate the amount of time an engineer would invest in finding out the cause and effect of these relationships. So these are areas where AI and ML have gone into production in many of our customer base. Here's another example on the manufacturing, right? The previous two examples was on design and verification, and this one is on manufacturing, where either it be mass synthesis on the left or yield management on the right. AI ML can be used to look at fine small changes that can be detected early on to give better yield, right? So this is an example of how we are using AI ML on the manufacturing side as well. Now, to sum it all up in a way where I want to leave a key takeaways is that AI ML use cases have finally gone into production. After many years of research and use cases, we are now in production at these customers. We are seeing some good traction. Secondly, our customers are now more savvier to say that I want to try solutions built on AI ML because now they understand the value of data. They're starting to appreciate it. They're investing on their own some platforms to store data. So I think the industry is warming up in many form and shape. Finally, the deployment of applications are quite different than EDA. If you really look at how a conventional EDA product is deployed today is very different when it comes to AI ML. You need to worry about infrastructure. You need to worry about determinism versus non-determinism and things like that when it comes to it. Basically, not all problems can be solved with AI ML, but when you have the right mixture of a problem statement and data, the algorithm and compute when added to it can really yield very fascinating results for some very cool problems that exist in EDA today. We expect a lot more good news as we go forward, as people are innovating almost on a regular basis by deploying applications to production. It's a very exciting phase for EDA as it tries to use these technologies to bridge the gap of going to market. Now let's change the gear and move completely into a different vector, which is about how AI and ML can help us build better EDA products, especially in the area of software engineering. As I mentioned earlier, this parallel can also be drawn for RTL development, except that the data that is generated by RTL may be slightly different from what's there for software. So as I walk through this presentation, please try to relay the same idea and concepts into your existing domains. When you look at the systemic complexity that's happening today in the area of product development, you will probably relate to this. EDA has been an industry that's been writing code since the 1990s and late 1980s actually. The amount of code that's been written, I won't be surprised if you're in the top 20 in the world when it comes to number of lines of code managed by, in general, EDA. You can start to draw parallel to it as well in your own companies, either it be RTL or C or C++, doesn't matter. The exponential rise that happens on code size, number of tests, number of releases that we do now, number of people contributing to this software, and the number of sites that keep growing up across the globe. And finally, the cost, because we are always hungry for compute and storage. And this exponential rise really has to be tamed because it cannot be an exponential growth because companies cannot manage costs by building software or hardware. So we started to ask these questions many, many years ago on how can we improve the quality and the predictability of what we are building. At the same time, can we improve the productivity and efficiency of our engineers? And can we gain some insights from historical data? And lastly, how do you manage cost? The reason we need to be thinking about all of this is just to look at opportunities to ensure the return on investments based on what we put the engineering resources into is well managed. Now, we started to look at this problem from a point of quality to start with, and then of course there's productivity and productivity as well. And from a quality vector, traditionally, I think all companies pretty much look at the three top vectors. One, we do quality by design. All of us are have specs, we have plannings, we have planning meetings. We try to put together a good thinking model. We write our test plans. We look at how which team needs to work on it. How do you modularize your code? There's a lot of design going into a good quality thought process. And then we go into quality by validation. When the feature is complete, we do a lot of testing. We do a lot of failure analysis. We execute our test plans. And there's a lot of bugs that get found there during that cycle. And we validate them. We check them off. And then finally, when the product hits the market, we monitor the defects that come from them, right? We look at what kinds of bugs are being reported, how often, and we start to converge on them, being very responsive, having a good support model. So these are the three vectors we've been acting on. Effectively, what we have done in this process is built a lot of metrics, right? Either it be coverage convergence, either it be memory leak management, or it could be, incoming bug management. These are all metrics, and all of them are pretty much done in a silo if you look at it, right? Many metrics, many spreadsheets. But we started to look at it from a different angle. We wanted to see how AI ML can add a new dimension to this. We call it quality by analytics. And this is a journey that we started to explore. Let's go a little bit into why we need to do this. One of the things, if you look at the previous approaches, just quality by design, validation, and defect management, it's more about what happened or why it happened, right? It was really looking at the past data and taking actions on it. Of course, there is some aspect to the presence, which is, oh, can we alert when the number of bugs are high, etc. But we never go beyond that. We never go look at what could happen, right? What will happen? What can happen? So this is really where AI ML starts to come in and takes the insights and starts to add the prediction and the prescriptive mentality into whatever we're trying to do. And this is the exploration that Synopsys started doing using AI ML for using software development. Now, let's look into three aspects which I really want to call out here. We call it the multi-dimensional relationship between the three vectors: code, test, and bugs or defects, right? So literally, when you look at this story here, the story is told between what you see between these three vectors, right? One, you have to know your defect, right? When did it happen? What happened? You have to know your code very well, because many times the story that's written in the functions and the code and the files are quite rich. And even in the test, what kind of tests are you writing? How effective they are. So when you start to look at having a diligence around data coming from these information, you start to rely on a data-based thinking. For example, if you associate which code is fixing which bug, or what kind of changes you're making, and if you associate which test is covering which code, and finally when a defect comes in, can you associate which tests are being written to prevent that bug from happening again? So there is a convergence between these three vectors that you really ought to pay attention to. Now, what can you do with this data? Well, let's take a look. When you look at a developer world today, right, same parallel can apply to hardware development or software development. A developer writes code. I'm talking about the picture on the left here, right? He writes some unit tests. He does some regressions. He checks it in. And then he goes into a CI system, right, where it merges into a common pool, top of the trunk. And then there's a build that happens, a nightly regression happens. A failure gets identified because of his commit, and it goes back to developer. It's a vicious cycle. We never look at the opportunity for a developer here from his point of view. He has got massive code to deal with, massive tests to deal with. He does not know the change that he is making is really going to create an impact or not, right? So effectively, we need to look at it from the eyes of a developer. And Synopsys started to look at this problem and said, how can we assist the developer? How can we do a shift left strategy to make something effective for a developer so that we can catch issues early on? Now, we invested in a whole bunch of AI ML techniques at different stages of its development, right? We call it connected analytics. And on the left most you see code query, which is how can we learn from the code that he's writing? Can we predict risks of the commit that he's trying to make early on? can we do some exploration of the kind of test that he's writing? Then on the left, you see planning better. Can we correlate the specs that is written to some of the code and tests that he's trying to do? And then you see failure triage and bug triage, which is given that there's a failure, can automatically, using AI ML techniques, auto group them, predict which person caused which check-in problems. Can you automate some workflows? And once a bug is identified, can we identify similar bugs? Can we eliminate duplicates? Can we auto assign to the right person? So thus saving a lot of time and productivity. And next, intelligent test selection. Do we really need to run all the tests? Can AI ML help you to select only a few tests that we need to do? All right. Release analytics. This is about, given all of this, can you tell us the story on how this release is looking better than the previous release? Can AI ML look at patterns, identifying risks, identifying actionable alerts? And finally, you want to be predictable. So can it give you a score of a release? Can it tell you how soon you can converge and what risks you may have? So we invested in a lot of AI ML in improving these productivity applications. Now, here are some examples, right, of results that we saw. Here is what you see here is a code hotspot analysis tool, right? It identifies, looking at data coming from the code, which functions are hot, right? What it really means is that you're really looking for identifying, looking at various data points and saying that because we know that this code was modified by so many developers, it was used to fix so many critical bugs in the past, it was used by multiple teams, these are the tests associated with it, this is the kind of memory problems it may have and has been fixed in the past. We learn a lot about the history of a function. And we use this tool, AI ML techniques, to statistically come up with indexes or score for each of these functions. So now you know in the myriad of problems that you have, which problems to focus on first, because the ROI by fixing those are quite high. Here is a dashboard that gives you a heat map of a module, but we do it for all our source code. Now, in the area of bug triaging, we were able to use AI ML techniques to cluster similar bugs, and therefore we gathered rich intelligence about the root cause of many of these bugs given the past fixes. Not only are we able to route it very quickly to each of these areas, we are also able to identify common patterns of where these problems occur. Next, here is an example of code risk. When a developer is about to commit a fix, we are able to use all the past information, what kind of bugs were fixed in the past in the same function that he's trying to modify. So we can actually predict which other customers may be impacted with this change, which other dependent modules that he needs to fix because we have seen that happen in the past. Who should be the right reviewer? Many times we pick up our colleagues to be reviewers, but the right owner is based on the intelligence that we can gather who's made some complex changes in the function in the past, right? Are there any related bugs that can happen? And which targets and which tests we need to target? So we come up with what we call as a risk score analysis by putting together all of this into perspective. Okay, so this gives a good score at the time of commit, whether should we allow the commit to go in or do we do more diligence? And to our surprise, we found 80% of the commits are harmless. It's the other 20% which makes us put a very bureaucratic process to slow everybody down, right? So use AI ML to really predict how to organize yourself from a process perspective as well. Here's another example of AI ML. Here we use natural language processing. Many times the collaterals that we have is spread out. Today in the world of AI ML and big data, you have an opportunity to relate various different data sources, right? Because you can look at documents, you can look at key value pairs, you can look at simple text paragraphs from bugs, you can correlate to even code many times. So natural language processing gives you relevancy on what you're searching for, right? Relevant searches is the reason why it's different from it's different from a regular search machine. How do you speed up routing of issues? How do you eliminate duplicates? How do you improve documentation? All these factors are used by NLP techniques that come into play. Okay, so I would definitely urge you to look at NLP approaches to actually mine your data to give productivity and efficiency. Well, all this does not complete unless you have a good established unified data management strategy. I'm sure your teams are all looking at siloed data. You're looking at many point tools trying to solve problems. You're looking at simple dashboards. You're looking at poor visibility across the flow. I think the whole journey starts by providing a good unified data management strategy. Start there first. Put together a good data governance on how you want to store the data. Bring in processes that need to be there. And then your goal really is to look at a unified data system. Look at correlation. We call it connected analytics, as I mentioned earlier. You can actually do a data-driven analytics. You can look at fine-grained, visibility of your data. Real time is very key. And finally, you're able to scale. So you're literally looking for starting with a good data governance. Now, the key takeaways for this part of the section is that really the software development, hardware development is a big data problem. There is enough data. Look at the amount of data that your code is going to generate, your tests can have, your coverage runs can have, your regression runs can have, your bug database exists. One has to see it that way. And only then you'll start to see how much insights you can gain. And connected analytics, which is where the story is really told, right? In the intersection of code, tests, and defects. Tap into that convergence. You learn a lot. We cannot just depend on people anymore because it's almost impossible for one person to know what's going on across the play. People have become very siloed in their expertise. It all starts with a good data diligent approach, as I mentioned. And the process management, don't forget the process aspect because you need to connect the dots for you to have build a connected analytics environment. And start with the process, link things together. Once you start linking things, the journey starts and becomes very meaningful. And lastly, it's a paradigm shift and the way you think about it, right? And AI ML is definitely leading the way in many of these approaches because with the size of the data we deal with, you need algorithms like AI ML to look at patterns, look at how you can predict certain things. So definitely there's value in looking at AI ML when you look at quality insights or your productivity or your cost savings, right? I didn't go over all the examples that one can build with AI ML, but gave you a flair of how these things look at, right? So with that, I will conclude my talk. Thank you very much. It's my honor to be here as a keynote speaker. And with that, I'll open it for Q&A.